In section 12.6, we're going to discuss motion along a curve. This is getting back to our roots of finding applications to calculus in physics by looking at motion and in particular position, velocity, and acceleration. So first, let's suppose that r of t, the vector valued function, is a position function of a particle moving along some curve in 2 or 3 dimensions. From this position function, we can define the instantaneous velocity, the instantaneous acceleration, and the instantaneous speed of the particle at a time t by defining the velocity to be the derivative of r of t with respect to t. The acceleration will be the derivative of velocity, or the second derivative of position, r, and the speed is just the magnitude of the velocity function. Notice that it's also sometimes denoted ds dt, okay, which is kind of a special notation. The s is not bold because this is no longer a vector valued function, but a scalar function. So jumping right in, let's find the velocity, speed, and acceleration at the given time, in this case t equals 2, of a particle moving along the given curve. So let's begin with the velocity function, v of t. That is found by just taking the derivative of the position function. In this case, our position function is given parametrically. And so dx dt is going to be the constant 3, dy dt is the constant -4, and dz dt is the constant 1. So this is very unique in that this velocity function is independent of t. In particular, this would then also serve as the velocity specifically at t equals 2. If we were looking for the speed, we need only compute the magnitude of the velocity function. So that's going to be the square root of 9 plus 16 plus 1. So that's the square root of 26. Again, the speed function in this particular example happens to be independent of t. So this also serves as the speed at t equals 2. All right. Lastly, we want to find the acceleration. The acceleration is the derivative of the velocity function. Since the velocity function was constant in each coordinate, that means that the acceleration function is 0 in each coordinate, and thus this serves as the acceleration at t equals 2. So kind of a very simple problem to start out here with. Next, we want to work backwards. Suppose we're given the acceleration function, how can we then recover the position function if we have some initial conditions on both velocity and position? So let's take a look at this guy. So let's first begin by recovering the velocity function. That's going to be found by taking the integral of acceleration. Now I'm going to write this in terms of the angle bracket notation. If you like the I hat and j hat, that'll work just as well. So I'm going to integrate the vector 1 e to the negative t. And of course, this is going to be with respect to t here. So this is going to give me t plus c1 and negative e to the negative t. Let me fix that. E to the negative t plus c2, where c1 and c2 are some constant of integration. Now it's important that you remember to tack on a constant of integration in each component function, rather than just some plus c at the end when we were talking about real valued functions. What we know is the initial velocity, that at time 0, the velocity is 1 in the first component, or excuse me, 2 in the first component and 1 in the second. So now what I'm going to do is I'm going to evaluate the function that I just found for velocity, which I just highlighted in green, at t equals 0. So that gives me c1 and a -1 plus c2. This allows me to solve for c1 and c2. So c1 is 2. C2 is also 2. So I conclude my velocity function is 2 plus, is t plus 2 and negative e to the negative t plus 2. So we are one step closer to our final answer. This was one of the things we were looking for, the velocity vector, so I'll go ahead and box that in. So now we just want to follow this same process and reiterate it, this time solving for the position function. So we're looking for r of t. That's going to be the integral of the velocity function, always with respect to t. So that's the integral of t plus 2 and negative e to the negative t plus 2 dt. So we integrate each component function. That gives us a 1/2 t squared plus 2t plus, I'll call it d1 for some constant of integration. And I now get a positive e to the negative t plus 2t plus some d2 for that constant of integration. Now, using my initial condition, r of 0 is 1, negative 1. And if I plug it into the expression that I just found for r of t, I get out d1 and 1 plus d2. So this now tells me that d1 is 1 and d2 is negative 2. So I conclude that my position function is given by 1/2 t squared plus 2t plus 1 and e to the negative t plus 2t minus 2. This serves as our position function. All right, so we have an understanding of the relationships between position, velocity, speed, and acceleration. We would like to build on those topics. And so that brings us to the notion of displacement versus distance. All right, so first of all, let's talk about displacement. If a particle travels along a curve C in 2 or 3 dimensions, the displacement of the particle over the time interval from t1 to t2 is commonly denoted by this capital delta of r and is defined as your ending position r of t2 minus your beginning position r of t1. So it's literally only keeping track of the end point and the beginning point, and it's not really taking into consideration what is happening on the position function in between that beginning and end. If you don't know the position function r, but instead you know the velocity function, you can solve this in one fell swoop by saying that the displacement is the integral from t1 to t2 of the velocity function. So remember, velocity is the derivative of position. And so the fundamental theorem of calculus part 2 says that the integral of a derivative cancels out and gives you back that position function. So you're recovering r of t, and then of course, the fundamental theorem of calculus part 1 says plug in your upper limit of integration, subtract off your lower limit of integration. All right, so again, displacement is only keeping track of your beginning and ending position data points. It does not care if you go back and forth a million times in between. It only cares about where you began and where you ended and what the difference is between those 2 points. Now, instead, let's suppose that you really want to keep track of everything in between. What you might want to compute is the distance. All right, so again, if you're traveling from home to campus, and then at the end of the day, you go from campus back to home, your displacement is 0. You started at home and you ended at home, so there was 0 displacement. But most certainly, you traveled a distance, and your car odometer would tell you such. How can we recover that distance? The problem with displacement is our forward distance is canceling out with our backwards distance. So we want to somehow eliminate that cancellation. And how we're going to do that is we're going to look at the speed function, right? Which is always positive in this case. So rather than integrating velocity, we're now going to integrate the speed function. We're going to denote distance by s. And we're going to say that the distance s traveled by the particle from t1 to t2 is just going to be found by integrating the speed. So we're still going to integrate from t1 to t2, but instead of integrating dr dt, which is the velocity, now we're integrating the magnitude of dr dt, which is the speed function. All right, so let's take a look at what this looks like in an example. 28, we want to find the displacement and the distance traveled over the indicated time interval. All right, so we have this position function that's involving some cosine functions, and then we see our interval here is from 0 to pi. So let's start by calculating the displacement. That's the easy one. All I need to do is calculate r of pi minus r of 0. So let's go ahead and plug it in. What is r of pi? So cosine of 2 pi is 1. Again, cosine of 2 pi is 1, so 1 minus 1 is 0. And cosine of 2 pi is 1, so I have 3 plus 1/2, which would give me 7/2. And next, I want to subtract off evaluating r at 0. Cosine of 0 is 1. Cosine of 0 is 1, so 1 minus 1 is 0. Cosine of 0 is 1, so 3 plus 1/2 is 7/2. All right, so our displacement here is 0 units. We had no displacement. And I want to note here that this is a vector, meaning I went 0 units in all directions. To emphasize this, you might write this as 0, 0, 0. All right, now I'd like to come up with the distance traveled over this time period. And by the way, I didn't note this, but you could write this as delta r here. All right, so now I'm looking for the distance. In order to begin computing the distance, I need to first have the velocity and furthermore the speed function. So let me find the velocity function first. That's just the derivative of the position function. So I'm going to use the chain rule here, -2 sine of 2t. Then again, I'm going to have, in this case, a positive 2 sine of 2t. And then finally, I'm going to have a negative sine of 2t. All right, so this is my velocity function. Let's go ahead and compute the speed function. So that is going to be the square root of 4 sine squared of 2t plus 4 sine squared of 2t plus sine squared of 2t. So this comes out to the square root of 9 sine squared of 2t. And if you recall back in the previous section, I made a big deal about the fact that the square root of x squared is the absolute value of x. It ended up not playing a role too big of a role in the example in section 12.3, but it's super important in this section. Square root of 9 is 3, as it always has been, but the square root of sine squared is going to be the absolute value of sine of 2t. It is imperative that you put these absolute values in, so I'm going to emphasize it by putting red bars around here. If you forget them, you would get the incorrect distance, and we'll see why here in a moment. All right, now, what we know is to compute our distance, which is denoted s, we want to integrate from 0 to pi our speed function. So that's the integral of 3 absolute value of sine 2t dt. Now we don't know how to integrate the absolute value function. So what we need to do is we need to break this down and we need to identify, well, when is sine of 2t positive, in which case we can just drop those absolute values, and in which case is sine of 2t negative. which means the absolute value changes the sign and thus kicks out a negative. So before we go that route, and I'm going to write in a different color here, let's first talk about sine of t, right? Without the 2 inside. We know that sine of t is positive from 0 to pi, and we know that it's negative from pi to 2 pi. And I guess you don't have to do the inclusive because it's actually 0 at 0, pi, and 2 pi, but you get the idea. So how is it affected when we include the 2 in here, right? So now when we look at that, remember, we only care about 0 to pi. This is our domain. So sine of t is positive on 0 to pi, but when you double that inside, it affects it differently. So we have that sine of 2t is positive or equal to 0 for 0 to pi over 2, right? Because if I plug pi over 2 in here, that gets me to sine of pi, and that's where it comes back down to 0. And I also know that sine of 2t is going to be non-positive from pi over 2 up to pi for the same reasoning, right? When you double the inside, you half the domain. And so I'm going to utilize this information and I'm going to say, look, if I'm from 0 to pi halves, that absolute value is doing nothing. So I'm going to say that this is the integral from 0 to pi halves of 3 sine of 2t dt. However, for the other half of the integral, my sine function is negative, which means that absolute value is actually going to negate the function to make it positive. So it becomes a negative 3 sine 2t dt. So again, what we're using here is the fact that the absolute value of x is equal to x if x is non-negative, and it's negative x if x was negative. So it negates the negative, making it positive. So this is super important. This is what we're using in order to break down this absolute value to these two individual integrals. All right, so now that we have this, it's just a matter of integrating. So we can finish it off from here. I'm just going to do this chain rule in my head. I'm going to kick out a 1/2 when I integrate. So this becomes a negative 3/2 cosine of 2t from 0 to pi halves. And this is going to become a positive 3/2 cosine of 2t from pi halves to pi. And so now we will just evaluate using the fundamental theorem of calculus. All right, when I plug in pi halves, it becomes cosine of pi, which is -1. When I plug in 0, it becomes cosine of 0, which is 1. And then similar over here. Cosine of 2 pi is 1. And minus cosine of pi is a -1. So I have negative 3/2 times -2 plus 3/2 times 2. So I have 3 plus 3 for a total of 6 units. All right, so if I zoom out a bit, we were displaced 0 units in terms of a vector here, right? So we did not change our endpoint was the same as our beginning point. But for our distance, we traveled 6 units overall. So just a difference there between the two. All right, we end the section talking about projectile motion parametrically. So we have supposed that we have an object in projectile motion. Now we're going to lay out some variables. Let S naught be the initial height, V naught be the initial speed, alpha be the angle that the initial velocity vector V naught makes with the positive x-axis, t be time, and g is the acceleration due to gravity, which we're using standard units, so 32 feet per second squared. Then we have the position function is given by, we have the x component here, V naught cosine alpha t. And again, that's just the horizontal position. The vertical position is your initial height plus V naught sine alpha t, and then due to gravity here, a minus 1/2 gt squared. You can also break it down to its x and y components as it's done here. So again, you can think of x as the horizontal component. You can think of y as the vertical component of projectile motion. All right, so our last example is working with these equations of projectile motion and solving a word problem. So I'm just going to clean up my equations here so they're not so messy. And let's take a look. We have a shell is fired from ground level with a muzzle speed of 320 feet per second and an elevation angle of 60 degrees. So before I move forward, let me just write out what we have. We're working with ground level here. So that means that our initial height, S naught, is 0 feet. We have a muzzle speed of 320 feet per second. That's our initial velocity. And we have our elevation angle, 60 degrees. I tend to think of things in radians, so I'll write that as pi thirds. All right, so what are we looking for? First, part A, the parametric equations for the shell's trajectory. B, the maximum height reached by the shell. C, the horizontal distance traveled by the shell. And D, the speed of the shell at impact. Now, I'll give you a quick warning here that there is not a lot of white space for the amount of work we're going to do, so please utilize your white space effectively. All right, so let's start here with part A. We just want to come up with the parametric equations. So starting here with our x of t formula, we have x of t is our initial velocity, which is 320 feet per second, times cosine of alpha, cosine of pi over 3, and this is times t. Now, if you're anything like me, I can never remember cosine of pi over 6 versus cosine of pi over 3, so I have to draw the special triangle every time. So here's pi over 6, pi over 3, and the right angle, 1, 2, square root of 3. So using SOHCAHTOA, cosine of pi over 3 is going to be adjacent over hypotenuse, so 1/2. So this is 320 times 1/2 t, all right, which is going to give me 160 t. This is one of our parametric equations. All right, the other one, y of t, is going to be our initial height, which is 0, plus the initial speed, 320, times a sine of pi over 3. This is times t. And then minus 1/2 g t squared. All right, so using our special triangle, this time we have sine is opposite over hypotenuse, so opposite and hypotenuse. So I have 320 times root 3 over 2, so that's going to be 160 root 3 t. And then I have minus 16 t squared. So I now have my two parametric equations for motion. All right, so we're going to use those throughout the rest of these problems. Part B, I want to find the maximum height reached by the shell. So if you think back to Calc 1, how would we go about finding maximum and minimum values? Remember that maximum values occur at a peak of, say, a mountaintop, and that occurs when the derivative equals 0. So to find a maximum, we want to find a derivative function and set it equal to 0. Well, which function are we looking at? We're trying to find a maximum height. So that's a vertical distance. So I'm going to say that y max occurs when the derivative function y prime of t equals 0. So that being said, let's go ahead and take the derivative here. Y prime of t is going to be 160 square root of 3 minus 32t. And I want to set this equal to 0. So I get t equals 160 root 3 over 32. Now let's see, this is gonna, if I divide by 16 everywhere, that gives me a 2 and a 10. So it looks like this whole thing is gonna reduce to 5 square root of 3 seconds. All right, now this is the time at which the max occurs. To actually find the maximum height, I need to evaluate the height function at this time. So y max is going to occur at y at 5 root 3 seconds. So I'm just plugging this into the y of t formula. So that's 160 root 3 times 5 root 3 minus 16 times 5 root 3 squared. All right, so this is 160 times 5 times 3, 15. Minus 16 times 5 root 3 squared is going to be 25 times 3, which is 75. So if I factor out a 16 here, I have 10 times 15 minus 75. So that's 16 times 150 minus 75, or 16 times 75. I don't know what that is, but I know that that's 8 times 150, which is 4 times 300, which comes out to 1,200 feet. Ran out of space, but I'm squeezing it in there. So the maximum height of this shell is at 1,200 feet above ground level. All right, next part, I want to find the horizontal distance traveled by the shell. I'm talking about a horizontal distance here. So this is going to be the x of t function. And I want to know the total distance traveled. So in order to start computing that, I need to first know, well, exactly how long did it take for the shell to hit the ground? Because the horizontal distance is going to be from the initial launch until that shell hits the ground or impacts. So my question is the following. What is x of t specifically when the shell hits the ground? In other words, when y of t equals 0. All right. So first of all, I need to find out, well, when does our shell hit the ground? It hits the ground when its height function is 0. So I'm going to set the height function equal to 0. I can factor a 16t out. That leaves me with a 10 root 3 minus t equals 0. So I get two values, t equals 0, which makes sense because the shell started at ground level, and then t equals 10 root 3 seconds. So it began at 0 height and it ended at 0 height after 10 root 3 seconds. So now all I'm going to do is I'm going to evaluate the x of t function at that 10 root 3. So x of 10 root 3 is the following. 160 times 10 root 3, which is going to give me 1,600 root 3 total feet. So that is the horizontal distance this shell traveled until impact. Finally, we want the speed of the shell at impact. We already determined that impact occurred at 10 square root of 3 seconds. So I just want to evaluate the speed function at that time. So to get there, I need to first find the velocity function, which is the first derivative of the position function. So I get 160, and then I get 160 root 3 minus 32t. All right, now what I'm going to do is, rather than taking this v of t function and finding the speed function in generality, I'm going to instead evaluate the speed function at 10 root 3, and then I'll take the magnitude of this velocity vector. So this is 160, and this is 160 root 3 minus 320 root 3, which is 160 comma negative 160 root 3. Now, to make my computation easier, let me factor out a 160, and this becomes 1 and negative root 3. Finally, evaluating the speed at 10 root 3, I have 160 square root of 1 plus 3, which is 160 times 2, or 320 feet per second. So this shell was shot off at a speed of 320 feet per second, and it landed at impact at that exact same speed. All right, so this concludes our notes over section 12.6, motion along a curve, and this concludes our notes for chapter 12.